Hello everyone, I'm Sitong Liu from Northwestern Polytechnical University. Today I will give a short tutorial about the mobile machine learning. It contains 4 parts: the background, major challenges, existing efforts, and the preview of the MobiSys mobile machine learning session. As we know, the machine learning and the cloud computing have stimulated a lot of intelligent applications on a wider range of mobile and IoT devices, such as the image recognition, the motion tracking, the human activity estimation, the language translation, the augmented reality, the virtual reality, art and creativity, on some smartphones, wearables, and smart infrastructures. However, they cannot work well under a poor network condition or the strict latency and privacy constraints. To this end, there is a growing trend to bring the machine learning, especially the deep learning-powered intelligence, to mobile devices. However, it is non-trivial to design and deploy the computation-intensive machine learning methods on the resource-constrained mobile and platforms. In view of these challenges, the resource-efficient mobile machine learning has been widely investigated to shrink the computation and size of the original machine learning model while remaining the desired accuracy, such as deep model compression, AutoML, dynamic inference, and adaptiveness. And here we summarize 3 major problems on the mobile machine learning. The first one is how to balance the specific mobile application performance demands and the mobile device constraints in detail. Where mobile system guides should not only consider the algorithm-dependent metrics such as the accuracy, but also the underlying platform relative metrics such as the energy cost, inference latency, and also they have the hybrid dependency. In particular, optimization of multiple objectives and resource constraints is non-trivial, and the measurement of platform-dependent performance metric is not straightforward. We argue that the widely used parameter number, Mach amount, or the speed-up ratio are not good approximations for the hardware efficiency, which heavily depends on the memory, movement, and the bandwidth bound. The second challenge is how to reduce the information redundancy and fit the input during inference, because the one-fit-all deep model is always redundant during inference. We should consider which deep model layer, channel, branch is important or redundant, and which input area or duration is more informative. And the third challenge is how to jointly inference across multiple cloud, edge, and end devices. Searching for the proper and balanced computation task among multiple devices is difficult. And also we summarize 2 typical study directions on the resource-efficient machine learning on mobile devices. On-device intelligence is to execute the machine learning inference at the local mobile device, and the distributed inference is to conduct the machine learning inference with distributed mobile data or device. The on-device intelligence include the deep model compression, knowledge distillation, AutoML for deep model compression, dynamic inference, platform awareness, machine learning, and system optimization. And the distributed system include the serial collaboration, parallel collaboration, and the multitask collaboration. On the other hand, we can also incorporate the machine learning into the edge devices for dynamic and adaptive system maintenance and management. Therefore, we also summarize another two typical study directions on the intelligence-enhanced mobile machine learning: the system management and the distributed learning. System management is to leverage the proper machine learning model for optimizing mobile systems, such as the sequential decision, the adaptive data catching, and the distributed learning is to train the mobile machine learning model with the distributed mobile data or devices, such as federated learning, continuous learning, meta-learning, and transfer learning. A representative research work of the deep model compression is the deep compression. Song and other authors present the pruning, quantization, and Hoffman encoding pipelines to reduce the resource cost of deep model. And then the researchers introduced the SVD and the depth-wise convolution composition-based low-rank factorization to decrease the computation amount and storage. Here, we have an insight that the convolution layer dominate the computation amount, while the fully connected layers dominate the storage. And then the NIN network and the SqueezeNet present the compact deep model architecture, including the multiple convolution, the global average polling, the squeeze, and the expand blocks. They focus directly on the problem of identifying the compact architecture with fewer parameters but equivalent accuracy compared to the well-known model. FaceNet and FSP explore the knowledge distillation of DN in the training phase. The knowledge distillation approach can obtain small and faster to execute models, and it has shown that a student network could imitate the soft output of a larger teacher network or the ensemble of the networks. A recently explored solution space lies in compressing the deep model in some manner before use on the device. Deep IoT proposed a new compression solution. A contribution of this work lies in exploring novel RN-based compressor to solve this problem. And the ADDIP found that a single compression technique in existing efforts may not suffice to meet the diverse user demands on the generated deep model. DN compression techniques should be selected on demand so that we can adapt to the diverse requirements and the constraints on accuracy, latency, storage, and energy cost. And this work presents an automatic compression framework that allows the user-defined criteria. It will benefit the development of deep model-powered mobile applications. It presents the reinforcement learning-based optimizer to automatically select the best combination of the DN compression technique. And the AMC leveraged the AutoML idea for model compression. It leveraged the reinforcement learning to provide the model compression policy. Multi-skill DenseNet investigates the image classification with computational resource limits at the test time. The authors train multiple classifiers with varying resource demands, and then they adaptively apply during test time to just select the best fitness at the test time. The SkipNet authors have an insight that while deeper network are needed to achieve the maximum accuracy. But for some inputs, the shallower networks are sufficient. Therefore, this work exploits the observation by learning to skip the convolutional layer on the per input pairs. And the neural architecture search, the NAS technique, today has attracted a lot of attention because it can automatically design the effective neural network architectures for specific domain tasks. However, the high computational cost of the convolutional NAS algorithms make it difficult to directly search the architectures on the large-scale task. The proxyless NAS addresses this problem to reduce the high memory consumption issue of the differentiable NAS and reduce the computational cost and still allow a large candidate site. In this similar thread of idea, the mobile NAS approach explicitly incorporates the model latency into the main objective of the NAS process, so that the search can identify a model that achieves a good trade-off between accuracy and latency for mobile tasks. To further address the challenging problem of machine learning inference across diverse devices with varying resource constraints, in this once-for-all work, the authors propose to quickly get a specified subnetwork by selecting from the OFA network without additional training. In addition to above-mentioned optimization of only the machine learning algorithm, they always assume a fixed hardware design and explore the proper neural architecture search only. We found that the co-designing of mobile machine learning algorithm and the system are also needed. For example, the MCUNet framework jointly designs the efficient neural architecture search algorithm, the TANI-NAS, and the lightweight inference engine, the TANI engine, to enable the ImageNet scale inference on the MCU platform. Another representative work is a novel hardware and software co-exploration framework for the efficient neural architecture search. This framework simultaneously explore both the NAS search space and the hardware design space to identify the best neural architecture and hardware pairs that maximize both the test accuracy and the hardware efficiency. Orthogonal to the on-device machine learning at the local mobile device, machine learning with distributed mobile data or devices is another direction. The serial partition and collaboration scheme is to offload the machine learning computation layer by layer. For example, the spine is a distributed inference system. It employs the mobile device and cloud computation together with a progressive inference method to deliver the faster and robust deep model inference across diverse settings. Different from the above serial scheme, the parallel partition and collaboration scheme is to offload the machine learning computation to multiple devices, and the difference is they calculate the result parallelly. For example, the MODN partitions the already trained machine learning model onto several the mobile devices to accelerate the deep model computation by alleviating the device level computation cost and memory usage. to broaden the application scale rather than the above model level collaboration scheme. The DIVS and EIF also explore the other level of loading method. For example, the DIVS present the task level of loading method. Finally, we will preview the 4 papers included in this mobile and this MobiSys mobile machine learning session and present their relevance to this topic. The first paper, ZTT, learning-based DVFS with the thermal throttling for the mobile devices. This paper is more like a case of the mobile machine learning for the intelligent system management. It leverages the deep reinforcement learning to management the DVFS. The cluster federated learning is a case of customized distributed learning of mobile machine learning. It is customized to the human activity recognition task, and the low latency speculative inference on the distributed multimodal data stream is more like a case of customized distributed system of the mobile machine learning. And the N-meter provides an important tool to predict the latency of the on-device machine learning inference on the mobile and IoT devices. The first paper is ZTT, and to fully exploit the CPU and GPU's capability on the mobile devices, we need to manage the heat generation and the power consumption. Therefore, the authors analysis how the mobile device's performance and the temperature characteristics will change with the applications and the environmental changes, and formulated this problem as a trade-off problem between the mobile device power consumption and the mobile application performance, with the hard constraints on the thermal threat. However, it is challenging to solve this problem due to the dynamic thermal environments and the diverse application performance requirements. The authors tackle this troublesome challenge in an adaptive and predictive manner. They propose a deep reinforcement learning-based dynamic frequency scaling algorithm. It is a case of leveraging the mobile machine learning for intelligent system management. The second paper is cluster federated learning, a similarity-aware federated learning system for the human activity recognition. We know the human activity recognition is one of the critical mobile application field. This paper focus on this field and leverage the federated learning scheme rather than the centralized learning method, because it can preserve the privacy of the mobile users' raw data. And the authors have a new finding that the global trend data model is not accurate for all mobile users, and their key idea is that there are intrinsic similarities among the mobile users' activity data, and this will help to reduce the cost of the federated learning. And then the authors analysis the impact of the cluster reliability of the mobile users' HAR data, and present a novel similarity-aware federated learning framework. This framework is customized for the mobile HAR application. Meanwhile, they optimize the communication performance among the distributed devices based on the learned similarity cluster structure. Therefore, we can regard this work as a case of customized distributed learning for the mobile machine learning. The third paper is the low latency speculative inference on the distributed multimodal data streams. Multimodal sensing has led to increased use on the IoT devices. This is because using the rich information of multimodal sensing data is more effective than that using a single modality in applications. While this problem is challenging, how to fuse the multiple model distributed data streams, especially they always have the different delayed time, and we want to achieve the efficient inference. Existing efforts either ignoring the data stream delay or blocking the inference pipeline always incur the degradation in the latency or accuracy. In view of this challenge, the authors present a novel speculative inference method on the multimodal data streams to adapt to the dynamic data stream delay. This paper we can regard it as a case of customized distributed system using the mobile machine learning. The fourth paper is N-meter toward the accurate latency prediction of deep learning model inference on diverse edge devices. Inference latency of on-device deep model inference is a crucial metric. However, we face a tough problem how to get the DIN inference latency. As we mentioned above, the measurement of the inference latency is heavily depend on the platform. Therefore, the challenge is on-device measurement on diverse edge device is too expensive. To address this challenge, the authors propose and design the N-meter, a novel and efficient system to accurately predict the inference latency of the same models on diverse edge devices, and they designed two techniques for the N-meter, including the operator fusion behaviors on the edge devices and the adaptive data sampling to reduce the cost of building such a kernel level latency predictor. This paper provides a tool to predict the latency of on-device inference of mobile machine learning. Thank you for your watching, and please pay more attention to the MobiSys mobile machine learning session, and more efforts and insights for the mobile machine learning topic are much needed. Thank you.